All right, guys, today our lesson is on what's called stoichiometry. So you guys, it's a technique that we use in order to figure out the amount of products that are produced or reactants that are used up in a chemical reaction. So there is a strong mathematical component here, so strap on your seatbelts because we're going for a calculational ride today. So anyways, it says, scientists predict that fashions will soon change so frequently, runway models won't be able to make it backstage before their clothes go out of style. Okay, you guys don't have to write this down, but you guys remember what a mole is. You guys remember a mole is 6.02 times 10 to the 23rd, extremely huge number. It says if you have 1 mole of pennies, and you were divided among the Earth's population, and if someone were to spend their share at a rate of $1 million a day, it'd take more than 4,000 years to spend all. Here's the idea, guys. Let's say we had a mole of pennies. So imagine a big pile of pennies, 6.02 times 10 to the 23rd. Remember, that's the chemist dozen. So then you get your portion of it. So you guys know there's around 7.5 billion people in the world. So let's say they divide it into 7.5, so let's say 7 billion equal portions. So you have your 1/7 billionth of that mole of pennies. If you were to spend all your pennies, you were to spend $1 million a day. So on Monday, you're like, okay, I'll buy that $1 million house. Tuesday, I'll buy that $1 million house. And you're spending $1 million a day out of all your pennies. It would take you 4,000 years just to spend all of the pennies that you have, which was just 1/7 billionth of that 1 mole of pennies. A mole is an extremely huge number. You guys, the last video lesson, we had this map here. Remember, it allowed us to convert between weight in grams, volume of gases, and number of molecules. And remember, all roads pass through moles. So we're going to take this one step further, and here's what we've got. We've got what's called, here's stoichiometry. You guys write this down, really important. Hopefully you guys see it looks pretty similar to the previous map. Really, what you see is really the only difference is it's kind of got two. So what stoichiometry is going to allow us to do is take information from one. Think of A as the reaction species that you have some information about, you know the value of, and you're going to use that to figure out B, which is your unknown. Okay. So really the only additional thing in this map is this center part here linking to a reaction species, and we call that the mole ratio. So I'm going to show you guys how we can use this. Okay. So here's the idea. Let's say you work for a toy company. You're a chemist for a toy company. You're like, why would a toy company need a chemist? Well, think you work for Mattel. One of the big hot items that Mattel sells are Hot Wheels. And you guys know the good Hot Wheels are probably made out of aluminum. So what do you guys think a chemist might serve there? What might the corporation want to know? Let's say a Hot Wheels, each Hot Wheel has about 60 grams of aluminum. But right, so here's like a block of aluminum. I didn't have a Hot Wheels, but let's just say every Hot Wheel car has about 60 grams of aluminum. You guys got to think, okay, where do we get the aluminum from? Well, you guys are probably guess, right? We get it from the ground. But contrary to what people might think, it's not like you can just dig in the ground and just find pure aluminum that we're going to use to make our Hot Wheels. You guys, it's actually going to be found in ore, and ore is, the metals are usually going to be combined. You guys remember, most things kind of interact with other things and form compounds. They don't usually exist in their elemental state. And in fact, where we get aluminum from is bauxite. Bauxite is aluminum oxide. Now, you guys, isn't that kind of trippy? This aluminum comes from this, and you guys see how it's like totally different properties, looks totally different. But that's what you'll find, they're unique properties. So, what a chemist might be able to be employed by, what Mattel Toy Company might want to know is when they're working with the miners, right, because they have to contract that out, so they kind of have to dig this up. What would we want to know? We might want to know, well, how much bauxite would I need to dig out of the ground to produce the 60 grams of aluminum that I need to make my Hot Wheel, right? Because that's all important to know, when they're making their product. So that's going to be our question. How much aluminum oxide, you guys, that's what bauxite is, aluminum oxide, is necessary to produce 60 grams of aluminum. Now, hopefully you guys see the progression in which we've been learning things. So from this, we should be able to even write out aluminum oxide from our nomenclature unit. So here's actually the reaction. So we actually start with aluminum oxide, okay? And what we do is we chemically break it down. So then you'd have to, and we're not going to talk about the chemical process, but you chemically break this down into, right, what do we want? Aluminum and oxygen. You guys remember oxygen's diatomic, okay? So, you guys, what we need to know is, whenever we're going to use a reaction and talk about an equation, you guys have to look at that equation. You have to recognize it's not quite complete. What's the problem with it? It's not balanced. Let me see if you guys are seeing everything that I'm seeing. Okay, yeah, you guys should be seeing that. It's not a balanced chemical equation. So that's the first thing we're going to do. So then I look, let's start with aluminums. I got 2 aluminums on this side, 1 on this side, so I'm going to put 2 here. So now my aluminum's balanced 2 and 2. Here I've got 2 oxygens here, but 3 here. What am I going to do? You know what? When you guys agree, that's kind of, there's no way you can get an odd number and then have it even. So you know what, when you have that kind of situation, you might have to go back, and you know what, just change another one. Just go back to this. Let's say, you know what, let me just make a coefficient here of 2. So obviously that's going to change my aluminum. So if I've got 2 of these, each with 2, when you guys agree 2 times 2, you remember take the coefficient times the subscript is 4, so that would be 4 aluminums. And now let's see if it'll work. Yep. To see how many oxygens I need here, I look here. 2 times 3, remember coefficient times subscript is 6. So I have 6 oxygens. If I start with 6, I need to end with 6. How many O2 molecules will give me 6 oxygen atoms? 3. So this is a properly balanced chemical equation. So now what I want you to do at this point, so you work with a balanced equation, you take any information in the problem itself and apply it to the equation. So I'm going to take any information here. Now notice it says, oh, I'm going to produce 60 grams of aluminum. So then take your information and put it over the corresponding substance. Now I'm not going to put it over this because this isn't aluminum, this is aluminum oxide. I want to produce 60 grams of aluminum, so I'm going to put the 60 grams over the aluminum here. And then you guys, there's always a question. You guys think about it, it says how much aluminum oxide? The question is, where am I going to put my question mark? What do I want to know information about? It says how much aluminum oxide. Where's my aluminum oxide? Oh, it's right here. And if I want to know how much, it doesn't indicate any specific unit, but I probably want to know the grams. How much of this aluminum oxide do I have to dig out of the ground that will ultimately be used to produce the 60 grams of aluminum? So I'll put that. Now at this point, guys, if you do it correct, I don't even need this anymore. I'm done. Now I can just look at this and I'm like, okay, how much of this do I need to produce that? Okay, now at this point, we've got this set up. Now we begin to use our map. So you guys remember, your A, think of your A, that's like your known, what you know information about. Your B, that's like your unknown. So now you think about it. So we're going to set up, we kind of have a unit analysis problem here, right? So you remember with unit analysis, we always do the endpoint first. What do I want to find? So I look at my question mark. I want to find grams of aluminum oxide. Okay? And I want to know how many grams of aluminum oxide. I want to know how many grams of this corresponds to what? 60 grams of aluminum. That's the information I'm starting with. So you guys, I'm going to go way over here because I don't know how many steps are involved in my, let me see if you guys can see everything. Yeah, you can, okay. I don't know how many steps are involved to get it from there to there. So now, once again, I go back to my map, okay? So look where I'm starting. 60 grams in my known, so where am I starting on my map? Oh, I'm starting at a weight. Starting at my weight of the reaction species that I know information about. And then where am I going? I want to get grams of something else. Oh, I want to figure out what the weight of my unknown is. So then, you guys, that just kind of tells us, it shows us how we accept our itinerary. So we just follow the map. I'm going to go from here to here, then to here, and then to here. You guys see? That is a 1, 2, 3 road journey. So I'm going to use 3 sets of parentheses. Okay. So the first word I'm going to take, I got to get from the weight of my known to the moles of my known. You guys remember what you do? You use what's called the molecular weight, or otherwise known as molar mass. So basically, I'm going to look up, here it's aluminum. I'm going to look up the molar mass of aluminum. I see what the weight is. It's 26.98. Round to the 10th place is 27.0 grams per mole. 27.0 grams per mole. So then that's going to go in here. Okay. Now, look, grams is on top, and I don't want grams. Remember, I don't want grams. I want to get to moles, so I'm going to put the grams on the bottom. 27.0 grams is equivalent to 1 mole. Now, you guys, here's what's another added thing that I want you guys to do. Before, I didn't really require it because we were dealing with one species, but now you guys see we're dealing with 2 different things. So you always want to keep track of what you're dealing with. So I would put in here very specifically what we're talking about. It is aluminum we're talking about. once again, if you don't do it, you can kind of get confused between the two if you don't write down specifically what you have. So now notice, look, grams of aluminum cancels. So now at this point, where am I at? I'm at moles of aluminum. You guys see? Moles of A. Now this is the new information, right? So far this has just been like conversions like we did on the previous lesson. Now, you guys, this is the big key to stoichiometry. This is the bridge that gets us from our known substance to our unknown substance. So from moles of A to moles of B. And it says what we do is we use what's called the mole ratio. And the hint is you use coefficients. So you guys here, just so you guys understand equations, here's what the coefficients tell you. When I look at this, it's saying 2 of these aluminum oxide units will decompose to form 4 of these and 3 of those. So now in this, you guys, the good thing is when you guys write the information here over the reaction species, regardless of how long your equation is, you only have to focus on 2 things. What are the 2 things that we're interested in? These 2, right? I'm not even worried about oxygen, it's just these 2. So that tells me, oh, I'm going to use the coefficient for those 2. And what is the mole ratio between those? 2 of these will produce 4 of those. That is the mole ratio. So then the question, so I'm going to put that in here. The question is, which one goes on the bottom? Well, look, moles of aluminum, I want that to cancel, so what am I going to do? I'm going to take 4 moles of aluminum. For every 4 moles of aluminum produced, it requires 2 moles of aluminum oxide. Now check it out, guys. Moles of aluminum cancel. And now notice the unit we have left is moles of aluminum oxide. That's moles of my B. See how we're just kind of moving along this path here. The last thing I got to do is convert moles of B to weight of B. And once again, what's the link between moles and weight? It's the molecular weight. But this time I got to get the molecular weight of aluminum oxide. So you guys remember what you do? You add up all the individual atomic weights. Aluminum weighs 27, but there's 2 of them, so 27 is 54. Oxygen, if I look on mine, weighs 16, but there's 3 oxygens. 16, 16, and 16, or 16 times 3, it's 48. 48 plus the 54, just kind of doing it in my head, that's 102 grams per mole. You guys, write it out if you didn't quite follow what I'm saying. So I'm going to put that in here. So notice, look, mole is on top. So which one of those do I want to put on the bottom? I want to put the 1 mole. 1 mole of aluminum oxide would weigh 102 grams. Notice I'm writing the name, so I keep track of what I'm doing. And you guys look, moles of aluminum oxide cancel, and what am I left with? You guys check it out. Grams of aluminum oxide, and that's what I wanted here. So now I'm ready to punch my numbers. Remember, multiply all the top, divide all the bottom. I get 60 times 2 times 102 divided by, you guys right, divided by 27. And then careful here, guys, it's on the bottom, so I divide again, divide by 4, and then I get 113. All right. So you guys, what did I just figure out? Hopefully you guys see. What I just figured out is it takes 113 grams of aluminum oxide. That's how much aluminum oxide I have to dig out of the ground, 113 grams, in order to extract 60 grams of aluminum from that. I can get 60 grams of aluminum. Theoretically, I can get 60 grams of aluminum from this 113 gram aluminum oxide. All right, you guys, this is way too difficult to just do one with you, so we're going to do one additional one. Okay. So here's the scenario. Let's do a scenario. Let's say there's an earthquake, and you guys are in the classroom, and you guys know in an earthquake, right, the electricity is going to go off. It's going to be super dark. And let's say Mr. Willitson has the bright idea that we can't see anything. Let's say our cell phones are damaged or whatever like that, and we can't see. We've got, the whole, like, let's say the classroom's like crumbled in on us, and we're just kind of like, under the rubble. I mean, kind of a horrible situation. But what we can do is, I know of a reaction. One second, guys. In which I can use magnesium. I think we've seen this before, and I can light it. So let's say I stumble into my back room and I find some magnesium, and then I light it up. And then you guys are going to see why I can use this. Check it out. And then it would be super bright, and then I could like look out and I could kind of see my students, if, which one of my students is alive, Okay, so you guys can see a big bright light, and what's happening is, here's what's happening. Okay, so you can see I'm going to produce the light. So you guys, and you know what? This is where a chemical equation can help you. You guys, this is one thing you guys should know. Whenever a lot of times we get a lot of heat or something given off, a lot of times you think about, what do you think, much like if I was to burn paper, what's the paper reacting with? What do you guys think the magnesium is reacting with? It's reacting with oxygen, okay? So what do you guys think might be a, kind of been a dumb thing, right? Obviously it produced the light and that would allow me to see, in the rubble and all that. But what do you guys think might have been a kind of the bad thing to kind of implement that reaction in our scenario? You guys think about in an earthquake when everything's crumbled down, you think about, you guys, if people don't die from like the initial impact, right? That's why we crawl on our desks and all that. What do you guys think people might die from? A lot of people think like starvation or whatever, but no, usually, after a few hours or a few days, you'd kind of be dug out, right? If people come to your rescue, but what could you die of? Can't you die of suffocation? And you guys, what did we use up in this reaction? Didn't we use up some of the valuable oxygen that might, right, still be in the classroom? So let's say that's kind of where I'm going with my question. Let's say we want to know how much, not that we would be doing calculations if we were in an earthquake, of course, but let's say that's what the question is. We want to know how much oxygen did we end up using up? Let's say that magnesium there, I didn't use up that much. Let's say it was just like a 0.5 gram sample. Okay, so once again, what do? We have to use a chemical equation. Guys, I'll usually give you the chemical equations, but it's pretty easy. Magnesium reacts with oxygen, and I think a lot of you guys could even figure out what you guys think is produced. What is this stuff right here? Oh, I don't know if you guys can see it, but it's actually a crumbly white solid. And you guys remember what things are brittle? Remember what we learned in bonding? Ionic compounds. And what are ionic compounds? Metals and nonmetals. What happened is the magnesium and oxygen combine together to form an ionic compound. So let's say I want to know that. Before, and you guys remember, before we use our equation, you guys got to remember, what do we have to make sure? We have to make sure it's balanced. So let's make sure it's balanced. I look at magnesium. I have 1 here, and check out magnesium here, it's 1. So let's say I just put a 1, okay? Now the last thing I got to do is balance oxygens right here. So I look here, there's 1 oxygen, but here oxygens come as a pair, so you guys can probably see, you know what? Sometimes you have to go back and change it. So rather than make it a 1, let's say I make this a 2. Obviously that's going to mean 2 magnesium, so I have to go back here and change this. Now let's see if it works. Check it out, I got 2 oxygen atoms. If I am with 2, I need to start with 2. How many O2 molecules will give me 2 oxygen atoms? You guessed it right, it's a 1. Okay, so it's a 2, 1, 2. So now we have that. Remember, the next step I want you guys to do is take any information from the problem itself and put it over the corresponding part in your chemical equation. So notice we had 0.5 grams of magnesium. That was how much magnesium I originally burned, right? And so I don't put it here because that's magnesium oxide. I put it here. And you guys, where do I want to put my question mark? What do I want to know about? How much oxygen will react with? How much oxygen did I use up when I burned that, combusted that magnesium? Wouldn't you guys agree that the question mark should go right here? And you guys, a little different here. You guys, usually when we're dealing with gases, we don't talk about grams of gas. We'd probably talk about liters of gas. How much? What's the volume? So I would probably put L here, okay? Because I want to know liter, the volume of the oxygen that was used up. Now you guys notice, look at what we did. You guys see how it's kind of different than the one before? See, the one before, we had information about the product, and we wanted to figure out information about the reactant. And it could go the reverse. Maybe we had information about the reactant, and we wanted to figure out information about the product. But notice, it doesn't matter where things are. Here, I had information about one reactant. I want to know how much of the other reactant is used up when those react, so it can go either way. So now I set up a unit analysis. Oh, you guys remember, the nice thing is you only have to focus on 2 things at a time. Even though I have 3 things here, the only 2 things I'm focused on is right here. I'm not worried about magnesium oxide, just these 2. So I set up my unit analysis. Remember, you always do the endpoint first. What do I want to find? Where's my question mark? It's right here. Oh, I want to see how many liters of oxygen was used up. And what information do I have to start with? I want to see how many liters of oxygen is used up if 0.5 grams of magnesium reactant. Let me make sure it's still within sight for you guys. Yes, it is. Okay, good. Okay, so I don't know how long it's going to take, so I'm going to stretch it out. Usually it's going to be 3 steps, by the way. So look, I'm starting with grams of magnesium. So what am I going to start with? Weight of A. And then where do I want to go to? I want to go to the volume of B, liters of B. Once again, check it out, guys. Right? Typical 3-step unit analysis. So, first thing is I'm going to convert from weight of A to mole of A. You guys, and if you guys forget this, when in doubt, you guys think about what are we always converting with? What was always in the middle? It's moles. If you forget like where to go with what, if you kind of just get the default position, I'm going to convert to moles and then go from there. So, grams to moles. Once again, what am I going to do? I'm going to look to my periodic table. I look up the molar mass of magnesium. It's 24.3 grams per mole. So this I got from the periodic table. And then I'm going to put it in here. Gram on top, so I'm going to put the grams on the bottom, 24.3 grams. Remember what I said? Put what we're talking about though. Don't forget to do that. And that 24.3 grams is equivalent to 1 mole. You guys, whenever you have a mole, it's always a 1 with the mole. Okay? All right, so now I'm at moles of magnesium. I'm at moles of A, I need to get to moles of B. Remember, this is the gap. Bridges the gap between what I know and what I don't know. So once again, I use what's called the mole ratio. Look to the coefficients. 2 of these reacts with 1 of those to produce 2 of those. What's the mole ratio? 2 of these reacts with 1 of those. Mole of magnesium's on the top, so this time I'm going to put it on the bottom. 2 moles of magnesium reacts with, or is equivalent to, essentially equivalent to, 1 mole of oxygen. Right? That's the ratio between those two. Moles of magnesium cancels. Last thing, look, I got to go from moles of oxygen to liters of oxygen. I'm going from moles to volume. And then you guys remember this conversion? Remember, 1 mole of a gas occupies a space of 22.4 liters. That was from the previous lesson. So that's just a fact, so I'll put that. I take this information right here, and I put it in here. So the mole's on top, so I'm going to put the 1 mole on the bottom. Remember, always put the 1 with the mole. 1 mole of oxygen under standard conditions would occupy a space of 22.4 liters. Okay, you guys can see the last unit standing is liters of oxygen, which is what I wanted. Good indication I did it correct. Now it's a matter of just punching numbers. So I multiply everything on top, 0.5 times 22.4. Then I divide by 24.3. And lastly, I divide by 2. Everything on the bottom you divide, and I get 0.23 liters, 0.23 liters. So students might have been mad at Mr. Willardson for using up the valuable little bit of oxygen we had left, but then I would come back and go, hey, you guys, I only used up, less than 1/4 of a liter. A liter's, well, I don't have anything here, but I didn't use up too much oxygen, so don't hate me. Okay, so that's how much 0.23 liters. When I burned this, just going back to this, now this is just magnesium oxide, but when I burned the 0.5 grams, it used up 0.23 liters to combine with that magnesium. All right, guys, that's stoichiometry, so you guys are going to have to practice. Till next time.